So one-sided limit is a way for us to describe the function's behavior from just the left side or just the right side of an x value. When we talk about limits in the past, we always talk about from both sides, right? In order for a true limit to exist, the graph has to approach the same y value from both sides of our target, right? So that still stands, but sometimes we want to be able to give a little bit more detail about how each side is behaving in terms of, if they're going to different y values, just being able to provide some additional information can be helpful. So let's say we had a function, a piecewise function, that's defined by two separate expressions. You got x squared, which is a parabola, but this parabola is not showing its full graph. It's only, because it's being restricted where the domain, it's only showing the graph to the right of 1. And we have x plus 3, that's a linear graph here. So this linear graph is only showing to the left of 1. So we see that there's a disconnection going on here. So I'm going to use what we've done in the past to show that the limit doesn't exist, because I'm going to pick a point to the left of the x value of the target. I'm going to pick a point to the right of the target. My target is 1 because I'm doing the limit as x approaches 1. And then from these points, I'm going to move towards my target. I'm going to move towards 1. So from this point, from the point on the left, I'm going to move to the right. From the point on the right, I'm going to move to the left. And we can see that these arrows are obviously not pointing, or they're not getting closer towards the same y value. So we simply say the limit does not exist. So we learned that, right? We learned how to determine whether a limit exists. But what I did with these arrows is kind of informal, right? It's kind of a visual way of representing how we do limits. But now we're going to show how we can represent this in a more formal language, more formal notation. So that's where the one-sided limit comes in. So one-sided limit is going to describe how this is behaving. And then it's also going to describe how this is behaving separately. So first up, we have the left-handed limit. That just means that in this case, you see how there's a negative sign here sitting up in the exponent location. And that negative means that I'm approaching 1 from the left side of 1. So that's what I did with plotting that point. That point indicates that I'm starting to the left of 1. That's my starting point, left of 1. And then I'm going to move towards 1 from that point. So that's why I drew the arrow to the right, because I want to approach 1 from that point. And as I approach 1 from that point, I see that my arrow is getting closer and closer towards a y value of 4. So that's my one-sided limit. Okay. Now, I could care less what's happening at that point. I just want to know what it's getting close to, right? So whether it's a hole or a filled-in circle, our one-sided limit is going to exist, because we just want to know where this arrow is pointing towards, or where that arrow is getting closer towards. Now, right-handed limit is where we are starting at the right side of 1. You see that plus sign there? That plus means that we're starting to the right of our target. And then we're going to move towards our target. We're going to move towards 1. So that's why I moved to the left. And as I move towards 1, I see my y value is getting closer towards 1. So that's my right-handed limit. So instead of just saying the limit doesn't exist, well, in addition to saying the limit doesn't exist, we can provide much more detailed information as to how the graph is moving. We're basically translating these arrows that we drew into a more formal representation. Right. All right, any questions with one-sided limits? Now let's say the graph looked like this. And we want to approach C from both sides. And let's say they are in agreement. If they are in agreement, this is approaching the same value as this side. So obviously, if the one-sided limits are in agreement, then we can say the limit does exist. All right, so depending on whether these agree or not agree, we can conclude whether our limit exists or not exist. So let's talk about this concept of continuity. A function is continuous if we can draw the graph without ever lifting our pen or pencil. Okay. So this is not continuous, right? Because if I draw this graph here, I have to lift my pen or pencil up at the hole, start up again on the other side of the hole, and then continue with the graph. And this is also not continuous, right? I cannot complete this entire graph. I can't draw this entire graph without lifting my pencil or pen or pencil. Right. Now, I think if we're looking at a graph, it'll be easy to tell whether the graph is continuous or not, because we just look to see if there's any hole, there's any breaks, right? But if we don't have the graph in front of us, it's nice to have kind of a way to step through and decide whether a limit exists or not, simply by using what we know about algebraic expressions and being able to fit it into these notations. So this is how we're going to show a function is continuous using limits and using these notations. So in order for a function to be continuous, it has to be able to meet all three conditions. Okay. So the first condition is, does the point exist? So as I go through these conditions, I'm just going to draw an example, sketch an example, and kind of talk through what each of those conditions could look like. Does the point exist? So let's say the graph has this, so it would be true, right? Point exists. Does the limit exist? Does the graph approach the same y value from either side of C? So let's say the graph looked like this. And if the graph looked like this, we would say, yes, the limit exists, because if I choose points on either side of C, and if I follow the path towards C, they're both pointing to the same y value, and this also checks off. But then the third condition is where we run into some trouble, right? The third condition is saying, does the limit exist where the point exists? Does the limit exist at the same location as the point? We see the limit exists at this location, but the point is defined at a different location. So obviously there's a break, right? We would say that because the limit as x approaches C of f of x does not equal to the point, our function is not continuous at x equals C. I just want to kind of talk through what it would look like if we were to step through a continuity condition for this graph. Okay. And we know this is not continuous because you cannot graph this without lifting your pencil, right? If you were to draw this, you have to draw it to this point here, pick up your pen, plot this point, pick up your pen again, drop it down to the graph, and continue moving forward. Now, let's say the graph looked like this, where the point exists, the limit exists, and in this case, the third condition would also pass because the limit does exist where the point exists. The hole that was created by the limit is effectively getting filled in by the ordered pair. So if this was our graph it would pass all three conditions, and we can sketch this graph without lifting our pencil, right? Because the graph is connected to the point, that point is getting filled in, and then we continue to the other side. Okay, any questions so far? Let's talk about the different types of discontinuity. Sorry, I made a typo here. Types of discontinuity. We have two types of discontinuity. The first type is removable discontinuity, and that just means that there's a hole in the graph. And this is a graph where you're 1 point away from achieving continuity. If I can remove and change 1 point on the graph, and if I can achieve continuity by just changing something about that 1 point, then I have a removable discontinuity. So if you look at this graph here, this graph is only 1 point away from achieving continuity, right? Because that hole there, if I filled in that hole, then all of a sudden it's continuous. So let's step through the conditions for this one, and I want to kind of talk about where we stop and what we look within the condition, within our continuity conditions, what does it look like to achieve this type of discontinuity? So let's say we had some C value, and let me make that the location of that hole as a Y value of 2. So let me just step through the conditions to kind of get some additional exposure to these continuity conditions. In this case, you would say f of c is undefined. Right? We don't see any point that sits there. Second condition, does the limit exist? Yes, right? If I choose 2 points on either side, and if I draw arrows from either side, they're both going to lead me to the same location. So the limit as x approaches c from the left side of c of f of x is equal to 2. From the other side is also approaching 2. Therefore, we conclude the full limit exists. So if you're dealing with a removable discontinuity, your second condition is always going to pass. Now, the first condition, we don't have to have that first condition. It's not necessary in terms of, okay, so we have to, regardless of whether we pass or fail the first condition, we always move to the next one because we need information from the second condition if we want to gather any information about removable or the other type of discontinuity. So the second condition passes, we're going to move to the third condition. The third condition is asking, do these results agree? Undefined is not the same thing as 2, so therefore the third condition fails. And because the third condition fails, but it passes the second one, this is when we have removable discontinuity. So our conclusion. So here's the basic. I'm gonna I have this on the next page on the summary as well, but I'm gonna go ahead and just write that here. Right. So for any removable discontinuity, it will always pass the second condition but fail the third one. Okay. Any questions so far? Does that make sense? Okay, let's move to the next page and let's talk about the other type of discontinuity. And this is where we call it non-removable discontinuity because it's not as easy as just changing one point. We're going to do a lot more if we want to make a non-removable discontinuity a continuous function. So a non-removable discontinuity, same thing as another name for it is step continuity, or sorry, step or jump discontinuity. And this is where this is a discontinuity where the graph is going to jump from one connected piece to another. Okay. And then I want you guys to write this down as well. Vertical asymptotes is also an example of non-removable discontinuity.
She's going to love you more than anything. I mean, she's been so appreciative of your videos.
Awesome. Thanks, Chip. Okay, so vertical asymptote is another example of non-removable discontinuity. And but this discontinuity is going to fail the second continuity condition. Okay, so let's talk about what that looks like. If we approach 1 from the left side of 1, sorry, negative 1 from the left side of negative 1, and then negative 1 from the right side of negative 1, we see this one is approaching 3. This one is approaching negative 1, sorry, positive 1. And because these don't agree, we know the limit doesn't exist. And whenever your limit doesn't exist, we can stop and we can say we have non-removable at x equals negative 1. Okay, I'm going to recap everything down here, but any questions with non-removable discontinuity? Basically, it's just the limit doesn't exist. If you can show that the limit doesn't exist, then you know what type of discontinuity you're dealing with. But if the limit does exist, then we got to dig a little further. We got to look at that third condition. Okay, so here's the recap before we jump into our example. So here's what we do first. We always plug in that point to figure out if that point exists. And then that C value is always going to be given to you either explicitly or implicitly. You shouldn't have to guess what point the problem is asking for you to focus on. So we should always be able to tell what X value the problem is asking us to focus on. So if we plug in, if we try to find that order pair, it's either going to exist or it's going to not exist. Regardless of what we get, we're going to have to move to the second condition. Okay. If the first condition fails, we know the function is not continuous, but we still don't know what type of discontinuity. So we still have to move forward. So think of the first condition as you're just gathering information, but it's not going to, but we can't just stop after the first one, regardless of whether the point exists or not. We're going to continue to test our next conditions because we want to categorize as removable or non-removable. Okay, so we gather information about the order pair, and now we're going to move to the second condition. Did I lose you guys? Do I still have you? I just don't know based off of my other screen here.
Yeah, you're good.
Okay, all right.
Yeah,
thanks.
we're good.
Yeah, my other screen is freezing up. I just didn't know whether you guys are affected by it. Okay. All right, so second condition is where we test for the limits. Okay, if the limit fails, then we can stop because we know exactly what type of discontinuity, right? It's going to have to be disconnected graphs, either like this or like a vertical asymptote. So if your second condition fails, you know exactly what type of discontinuity. There's no need to move any further. You can stop. But if the second condition passes, then we're going to continue searching for if there's a discontinuity. We're going to go to that third condition. So now when we get to the third condition, is simply deciding, does the hole that was created by the limit, is that getting filled in by the ordered pair from the first condition? Okay. If these are not the same, if they're not in agreement, then we know it has to be a removable discontinuity. That hole is not getting filled in either because the point is sitting elsewhere or the point doesn't exist at all. Now, if all three conditions pass, then we can confirm the function is continuous at that point. Okay. All right, let's look at each of these examples here. And it says use continuity conditions to determine reasons why the following graphs are discontinuous, then categorize as removable or non-removable. So the C value that we're going to be concerned with is going to be wherever we see the break in the graph. So because we have the visual graph in front of us, we can just find those points easily. And I meant for these to be holes here, so if you guys want to clarify that. So my first C value is 5, the second is also at 5, the third one is at 3. Now, right now, it may seem like a little bit redundant to have to go through all these steps when we can obviously tell what's going on. But right now we're just kind of practicing the notations, practicing writing things out, and then getting comfortable with each of the conditions. And then once we're comfortable with this, then we'll move on to problems where you're just given a function notation and you don't have the graph in front of you to guide you. You're going to have to rely on the results of these values to guide whether to move on, whether a function is continuous, and also what type of discontinuity. Okay, but right now we're going to have the graph to kind of help us visualize and get comfortable with these continuity conditions. Okay, so first things first, we have to find the point. The point, we know our C value is 5, so f of 5. What's f of 5 equal to?
One.
Just 1, right? So regardless of what you get from the first condition, you're always going to move to the second one. Okay, so we're never going to stop after just the first one. Because if the point doesn't exist, it could be a vertical asymptote, but it could also be a hole in the graph. We still don't know. But in this case, the point exists. Okay, we keep going. We're just gathering information with the first condition. Second condition is where we have to involve limits. But we're going to practice our notation with one-sided limits. So I'm going to put the arrows to kind of help give us a visual. Pick points on either side of 5, and then from both points, we're going to move them towards 5. And I'm going to translate these arrows into one-sided limit notations. So this arrow is the left-handed limit. And we can clearly see this arrow is getting closer towards 2. Again, we don't care what's happening at 2. We just want to know where it's approaching. It's approaching 2. The other side is going to be our notation for one-sided limit as x approaches 5 from the right side of 5. And we can clearly see this is not in agreement, right? This is a different value here. And then because of the information that we gathered, we can conclude that the full limit does not exist. And if the full limit doesn't exist, we stop because we know exactly what type of discontinuity we're dealing with. And when you say what type of discontinuity, make sure you specify the location, because it's not discontinuous everywhere, right? It's only discontinuous when we're talking about 5. I want to remind us about the notations again. I think it's easy for us to write this without the f of x. I think a lot of us want to write it this way because that's the way that we say it. We say limit as x approaches 5 from the left side of 5 equals 2. But this is incorrect notation. We need to identify what expression or what function we're talking about. We have to name that function. Okay. Either as a function notation or as something in algebraic form. Okay, any questions so far? We're just walking through the conditions here. Okay, let's look at part B. We're going to step through each condition and see if we can prove, using the continuity conditions, what type of discontinuity we're dealing with. Again, we start with f of 5. But in this case, f of 5 is not going to exist, right? There's a hole there, but there's no other point that's defined at 5. Second condition, does the limit exist? So we're going to practice using our one-sided limit notations. The arrows are pointing to the same y value, so they should be in agreement. So if we follow the path of this arrow, it's taking us towards a y value of 1. Follow the path of the other arrow, it's also taking us towards 1. So therefore, the full limit must exist because our approach are consistent. Second condition passes. So if it passes, then we move to the third condition. So now the third condition, all we do with the third condition is we look at what we gathered from first and the second one. And we just compare those values. Are they the same or are they not the same? Obviously, in this case, not the same. So we say the limit as x approaches 5 of f of x does not equal to f of 5. So if the third condition fails, we know what type of discontinuity, right? This is a removable discontinuity. This graph is only 1 point away from achieving continuity. If I fill in that hole, then all of a sudden it's continuous. So if you're only 1 point away, we call it removable discontinuity. Okay, questions so far? All right, third example. Stepping through our conditions again. Our point of interest is now at 3. Nothing on the asymptote, so also undefined, but we keep going. Second condition, does the limit exist? We're going to practice with our one-sided limit notation. So I'm going to draw 2 points, follow the path of the graph, and they're both leading me towards infinity. And we know infinity is not a real number, so this still categorizes as a limit doesn't exist, right? So our conclusion is limit as x approaches 3 of f of x does not exist. However, because these are in agreement, both arrows are going in the same direction, we can subcategorize it as a positive infinity. But ultimately, this is still a failure of second condition. So we can conclude we'll stop because we failed the second condition. We don't go to the third one. And we say non-removable discontinuity. And then make sure you name the location of your discontinuity. Okay, any questions so far with the notations, with the steps, when to stop, when to move forward? Okay, let's see if we can attempt a problem where we don't have the graph in front of us and we have to rely simply on function notation, algebraic expression. Okay. So it says, find the value of discontinuity for our function. Is it removable? If so, what will we need to do to set f of x equal for it to be continuous? And we're going to step through continuity conditions to support our answer. Now, we don't have the graph in front of us, but we have the function expression. Where do we search for a discontinuity? If you want to look for discontinuity, where would you look to find that? Where's the graph going to be undefined? Where do we look if we're trying to determine where the graph is undefined?
If the denominator equals 0.
Good. So we look at the denominator. Denominator is where you look if you're trying to find places where the graph is undefined. Okay. Now, we don't know if it's a hole or an asymptote yet, or a hole or asymptote yet, but this is where we look for potential breaks in the graph. Okay, so we set x minus 3 equal to 0. We solve for x, and indirectly, we're now able to find our c-value. That's the c-value. That's our point of interest that we're going to be centered around. So now we're going to start building our conditions here. First condition, does the point exist? F of 3. Okay, we're going to plug that in. And if I plug 3 in, I get 9 minus 9 over 0 minus 0, and that is an undefined point. Second condition, does the limit exist? Now, we only have one function to deal with, so we're not going to have to need to use one-side limit. I would say you want to use one-side limit if you're forced to deal with two separate functions. Then the approach from the left and from the right are distinctly going to be different because you're looking at two separate functions. But algebraically, if you're just dealing with one function, it doesn't matter if you're putting from the left or from the right, it's always going to be the same. It's always going to be consistent because you're looking at the same function and you're dealing with the same point. So I'm just going to jump directly to just the full limit statement. Instead of writing f of x, I'm going to write out the expression. It's not wrong if you write out just f of x, but I think the expression is going to be more helpful because I'm going to go through my steps that I did from previous sections, right? I'm going to plug in, decide whether it's a hole, and then if there's a hole, I can go through factoring, I can reduce. So now we can revisit what we've been doing from past sections, right? So if I plug 3 in, I get 0 over 0. We know 0 over 0 is an indication of a hole. If there's a hole, we know our limit is going to exist. It's just a matter of finding that hole and removing it and then reevaluating it. Okay. X squared minus 9, difference of squares, so you can factor that. So we clearly see where the hole is located. The hole is now removed. We have a simplified expression. We plug 3 in for x, and we get 3 plus 3, which is 6. So this tells us that the limit exists, second condition passes, and if second condition passes, we're going to test that third condition. So third condition, all we do with the third condition is we're just doing a comparison. Let's look at what we got from the first and the second and look to see are they in agreement. If they are, then great. That means our function is continuous. If they're not, like in this case, we know that there's a discontinuity because the limit. So here I went back to f of x because I'm just referring to it. I'm not working through the problem anymore. But these are interchangeable depending on which will serve your purpose better. So obviously these are not in agreement. If these are not in agreement, third condition fails. Okay, thanks everyone. We will start 1.4b tomorrow.
Thank you, Mr. Yang.
Thank you. Have a great day, guys.
Bye, Mr.
Thank
Yang.
you.
Have a nice day.
Bye, thank you.
Bye, Mr. Yang.
Bye, thank you.
Thank you, Mr. Yang. Have a nice
See you
day.
guys.
Bye.
Yeah, you too. Have a nice day.
Bye, Mr. Yang. Thank you.
Bye, have a good day. You too.
Bye, Mr. Yang.
Bye, Vice Right.
Thank you.
See you.